Section 13.3, the fundamental theorem of line integrals, video 5. I feel remiss that I didn't actually summarize the important conclusion in the last video. So I want to start by summarizing the important conclusion at the end of the last video, which I said but didn't write. Basically said the following. A line integral is independent of path in its domain D. When I say domain D, I mean domain of the function f. If and only if. You've probably seen the if with two f's before. It's shorthand for if and only if. If and only if the line integral is equal to 0 for every closed curve C and D. If and only if means it's a biconditional, which means you can read this in both directions. If this happens, then that will happen, and vice versa. If that happens, then this will happen. Not all if-then statements can be written in both directions. For example, if you live in Tyler, then you live in Texas. But I can't say if you live in Texas, then you live in Tyler. That's an example of a conditional that is not a biconditional. So I wanted to summarize that. It was kind of important and it was worth writing on the board. This is actually Theorem 3 on page 775. But let's go back to the original question that we were asking about how do we know if a vector function is conservative, because if it is, then we can apply the fundamental theorem of line integrals and evaluate the line integral easily. And by the way, all of this setup for the fundamental theorem of line integrals, if I had time to get to it, is critical to the next section called Green's theorem. And for those of you going down the physics and engineering path, kind of an important theorem. We know that if a vector function f is conservative, in other words, it's equal to the gradient of some scalar function f, then the line integral of f dot dr is independent of path, according to the fundamental theorem of line integrals, where you just evaluate the integral at its endpoints. And as a consequence of being independent of path, then the line integral is equal to 0 for any closed curve C in the domain. But you'll notice I've underlined some parts in red. If vector function f is conservative, then the line integral is equal to 0 for any closed curve C in domain D. But is that a biconditional? In other words, can we reverse the implication? If the line integral is equal to 0 for every closed curve C in the domain D, then can we conclude that the function is conservative? And the answer is almost. Now, the reason I'm saying almost is that there's another condition on the domain that has to be true in order for this to actually be a biconditional. In other words, I have to impose another condition on the domain in order for being conservative to be equivalent to saying that your line integral is equal to 0 over any closed curve. The reason for this is really belongs in a class called topology, but I'll just kind of briefly explain what I mean, and I'll save you all of the topological nightmares. In order to reverse the implication and make this a biconditional, the domain D must be make sure I'm consistent with the author's terminology, open, I'll explain what that means in a second, comma, connected domain. Now, what do we mean by open and what do we mean by connected? Both of those words kind of have intuitive meanings. In topology, they have very rigid definitions. I'm going to meet somewhere in the middle. Open basically means that it does not contain its boundary. The strict definition of open, let's say this is domain D, the strict definition of open says if you pick any point on the interior, then there's a disk around that point that's contained inside the set. It may be a small disk, like if I pick a point really close to the boundary, then I would have to put a smaller circle around it, but it would still be contained inside of there. But based on that definition, the set cannot contain a point on the boundary, because if it did, any closed circle, any closed disk around it would have to intersect outside the exterior of the set, if you will. So that's the strict definition of being open, at least in R2, that if you pick any point in the set, there exists a closed disk around it that is also contained in the set. So that's what it means by open. Connected simply means if you pick any 2 points inside of the set, there's a path connecting them that is also inside of the set. So I can't have a domain that contains any points on its boundary, and I can't have a domain that's made up of the union of 2 disconnected sets, because I picked a point over there and I picked a point over there. I can't connect them without leaving the set, the set being the union of these 2 things. So as long as your domain doesn't contain its boundary and is connected, you're okay. Now, this domain can have a hole in it. For example, let's say we make this little fried egg shape, and then the domain is just all this over here. That would be an open connected domain, because A, it doesn't contain any boundary points, either on its outer or inner boundaries, if you will. And if I pick any 2 points inside, I can still connect them with a path that doesn't leave the set. In one more example, we'll get to a case where you can't even have a hole in it. But for now, if your domain is open, so it doesn't contain any boundary points, and connected. Now, by this definition, R2, the whole plane, is open and connected. There are no boundary points because it goes forever. Or you take any point, you can put a disk around it that's contained inside of R2, and it's connected because you can connect any 2 points in R2 without leaving R2. But if your domain is open and connected, then this does become a biconditional. So we can say the following for the reverse implication. If D is an open, connected domain, and the line integral over the curve C of f dot dr is equal to 0 for every closed curve C in D, then the vector function f is conservative. So what does this mean in terms of the fundamental theorem of line integrals? It means if your line integral is equal to 0 over any closed curve, then you can apply the fundamental theorem of line integrals over any other curve. Actually, over any curve, period. It doesn't even have to be not closed, because it would still come out to be 0. So we kind of have a biconditional. In this direction, it doesn't matter if the domain is connected. And before I say that, let me double check. Well, I've been kind of glossing over the topological aspects of the domain, whether it's closed or open, whether it's connected or not, up until now when they start making a big deal about it. So I will go out on a limb and say that the implication in this direction, if you're conservative, then your line integral over any closed curve is 0 for any curve C in the domain D. I know that it doesn't require both the domain be open and connected. I'm pretty sure we can lose the open there. I don't think we can lose the connected. But I'm not going to dwell too much on the topological aspects of this. Let's just say that you can reverse the implication if you have a couple of specific conditions on your domain. That was a lot to say. Now, what we just stated was Theorem 4 on page 775, and I'll read it to you, and it's pretty much this. It says, suppose f is a vector field that is continuous, so I left out the continuity, but we kind of always assume that. Continuous on an open connected region D. If the line integral is independent of path, oh my apologies, They actually state the theorem in terms of path independence, but recall from the previous video that path independence was equivalent to this. So anywhere we say the integral over a closed curve is equal to 0, we can say path independent. So let's cross this out and say that the integral of the integral over any curve C of f dot dr is path independent. That's equivalent to saying the line integral over any closed curve is equal to 0. So if you're an open connected domain and your line integral is path independent, then your actual vector function is conservative. Which means there exists a potential function lowercase f such that the gradient of lowercase f is equal to vector function f. How do we find that? We'll find out.